Hello everybody, welcome to another validation model. This week we're going to take a look at a flat rectangular plate where the two short sides are fixed and then two sides are simply supported and it has a uniform load. It does come from Rourke and Young, page 390, table 26, case 5A for the 1975 5th edition. Again, as I just mentioned, it is a flat rectangular plate. Short edges would be fixed, the long edges simply supported, uniform load. The length of the plate is 20 inches by 10 inches wide. The thickness is 0.1 and a pressure is going to be applied that's 10 psi. Material properties will include a Poisson's ratio of 0.3, Young's modulus of 30E6. We will use quarter symmetry. If you are watching these videos in sequence, I would agree that this one is very similar to the validation model that we did prior. The prior model was a flat plate. I do believe the dimensions of it were even the same. Thickness, if not the same, was pretty close, and it also had a uniform pressure. So what's different this time? What's different really are the constraints. And I debated doing this one because it is so similar, but at the same time, I think there is value in this validation model. And the reason for that is because we are constraining it differently. We're holding it differently. And if you are using these validation examples to make sure that the program is doing what you want it to do, maybe you're new to the Autodesk Inventor Nastran and somebody says, hey, how do we know there's this program that you want to use or you want us to utilize within our environment to do our FEA work? How do we know that it's producing the output that we want it to produce, that it's calculating appropriately? Well, that's part of what these validation examples are for. Part of this is if you have an interest in FEA, so you can learn a little bit about the Nastran capabilities and how to set up models. But at the same time, because they are validation models, that's why I generally choose validation models so that we can compare them to known output and make sure that the program is doing what it should do. I have confidence in that. I've been using the program for quite a while. Disclaimer, I also work for Autodesk professionally. In my career. This is something that I just do on the side for fun. But it also, I want to make sure that as we iterate on the software that we make the newest releases of the program, and I generally tend to stay current with the software to make sure that it is doing what it should do. So we will go through this exercise. If you're new here, welcome. I hope you enjoy the video. So let's go ahead and get started with the model. It is, again, a 20 inch by 10 inch plate. And I'm going to do a 1/4 inch symmetry, which means that I need to make a 10 inch by 5 inch wide plate. And I'm going to go ahead and move this Excel. Oh boy. Move this Excel off to the side here a little bit. We'll bring it back when we go to validate those results. So I'm going to go with starting a sketch. And looking at my mini axis, I am going to sketch on the XY plane. And then we'll sketch a rectangle. And that rectangle is going to go from the origin. And I'll just pull it out a little bit. And again, since we're doing a 1/4 symmetry, what I want is 10 inch. And then hit tab. And then the other dimension is going to be 5. So there's my 10 by 5 rectangle right there. And we know from there, since we are using shells, or maybe you don't know yet, in order to get geometry that will be shells, all I have to do in here is then patch that sketch region. So let's do that, and we'll say OK. So now that I have this surface model, when I take it into the Nastran environment, then I can apply a mesh to it and make them shell elements. So let's go ahead and save this model. Let me do a file save here. And I'm going to call this, let's see where I am in the list. I guess I'm at V13. So we'll call it V13 demo. And then I'm going to go ahead and select the environments and Autodesk Inventor Nastran. Before I do that, we should take a look up here. I am using 2022. And if I go to the pull down menu, I should be able to go to, oh, there it is right there, the About. And we can see that for the Inventor Professional, I'm using 22.2, so I am quite up to date Looks like it was released not very long ago. But anything that I'm going to do here, the point of that is anything that I'm going to do here with 2022, if you have a 2021 or 2020 or 19 or 18, all those versions should be able to do what I am about to do for this example. So if you do have a slightly older version that you are leveraging, don't worry about that. These are all pretty simple steps. So I'm going to go to Autodesk and Autodesk Inventor Nastran. That is one thing I will mention. If you're, let's say, back around 2018, it was called Nastran InCAD. There was a small name change called Inventor Nastran somewhere between, say, 2018 and 2020. I think it was at 2020, if I recall correctly. Not 100% sure about that. But again, just a small name change. The program is the same. All right, so coming into the Nastran environment, what we are going to do is a linear static model. So that's all good and well. I do need to create an idealization. So I'm going to go ahead and select idealizations. And over here in the top of the idealizations, we do not want solids. This is not 3D volumes. This is a flat planar region. So we want to do this with shell elements. And because I have a planar region, right? Remember the whole model is a 20-inch by 10-inch. I did a 10 by 5 again for the quarter symmetry, but we don't have any thickness modeled. So we do need to tell it what is the mathematical thickness of this plate? And that was defined for us in the problem as 0.1 inch. And then for the material, let's go ahead and select that button so that we can access the material. We could do something like select material. And I could go to the Autodesk material library and I'll scroll all the way down until we get into our steel and the ASTM, right? And those of you who watch my other videos, you know that I like to choose an ASTM A36, right? That's a start. It always gives me Poisson's ratio at 0.3. I'm going to change the modulus. Let's make that 3E7 or 30E6, same thing, right? In English inch units, 30E7 or 30E6 psi, and Poisson's ratio 0.3. So let's go ahead and say OK to that. So now my material is defined. This next thing is just the color of the mesh. Let's go ahead and leave that green. You can choose a different colored mesh if you want. I'm OK with the green today. Below that is the shape of the mesh, the shape of the elements that are going to make up our mesh. So since we are doing shells, we can tell it whether we want to have quadrilateral or triangular elements. I'm going to go ahead and leave it at quads, and we'll say OK. At that point, let's go ahead and generate our mesh and see what our default mesh gives us. I'm going to go with a little bit finer than that. So let's go into mesh settings, and let's see what a 1/4 inch looks like on there. It might be finer than I'm looking for. Yeah, not terrible. Let's go ahead and run with it. We'll say okay. Probably finer than we need, but we'll take it for now. I don't think it's a very large problem. The nodes, there's 2,500 nodes and 800 elements. That should run pretty quickly. All right, so what do we want to do from there? We still have to do our loads and we have to do the constraints on it. And then I think we will be just about ready to run. So let's go ahead and work, I guess, in a generally left to right progression. So let's go with our constraints next. We know that the short edges are fixed. So I'm going to say this outside right edge is my fully fixed. And let me go ahead and name that. The naming doesn't have anything to do with anything other than to help keep me straight with what the different constraints and loads are in the model tree. The actual, of course, settings for whether it's fully fixed or not depends on what I have checked in translation and rotation over on the right. And you can see by default everything's checked, translation and rotations. They're all fixed, so we'll say OK to that. Now the other short edge over here, had I drawn the full model, that would also be fixed, but this is a symmetry model, right? So we want to constrain the vector perpendicular to that. So let's go ahead and do a constraint there. And I'm going to first set it to free. And then vector perpendicular is x. We'll choose x symmetry. And then I'm going to go ahead and name that just to keep it straight in the tree. or browser. Let's say OK to that. So there we go. Let's move this over just a little bit. There we go. So in the Nastran model tree, under constraints, now you can see I have my fixed constraint and I have my X symmetry constraint. We'll make this edge our other symmetry edge, and then we'll make this the simply supported edge. So let's go constraints again. We'll select the top edge here. Vector perpendicular to that is the Y. So we'll choose our Y symmetry. And assign the name. There we go. And then on the bottom edge here, that is where we are going to do our simple support. So for that one, let's go ahead and do free. And since we're doing simply supported, what we are going to do for that is constrain it in the Y direction. And then also because we have a load perpendicular to this plate, normal to the plate, we're going to constrain TZ. There we go. In other words, we're allowing that X translation, and we're also allowing the rotations of that edge. And again, I explained it in the prior validation model. If you take a look at the video for V12, these little symbols, the glyphs that come onto the model, give you some insight into what you have constrained. So a single arrowhead like this, that's indicating a translation constraint. So, and it also points in the vector direction of the constraint. So this one, single arrowhead, I can see is aligned with the Y, so that would be my TY constraint. And then this single arrowhead aligned with the Z axis, so that's my TZ constraint. And then elsewhere on the model, like here, if I hover over it, you can see there's kind of a double arrowhead. That would be rotations, and that would be aligned with the Z-axis. So that would tell me that I'm constrained here, rotation about Z. And then there's my translation in the Z direction. Same thing here. This would be my, that's aligned with the Y. So that would be my Y translation, and then rotation about the Y-axis. All right. Moving on, let's go ahead and add some load to this model. This is going to be a pressure that we want applied to this, if I recall. Yep. And it's, let me select the entities, that surface, and it's going to be 10 psi. All right, and there is our pressure arrow. By the way, I've mentioned it before, but the number, I get this looks kind of like a force, so that's where I'm headed with this. We did apply a pressure. If I look at the load over here, if I hover over that load, you can see the little pop-up there. Near the model, it says 10 psi, so I can confirm that I have a pressure applied to it. It looks like maybe a force, right, just because of the single arrow. But you also notice that we have single constraints along the edges. That doesn't mean that just that point is constrained. And you can certainly adjust, how big these things are and how many are on your model. So if you want that to look more like a pressure distributed over the model, let's go to Edit on that load. And here we can adjust the size of it. So maybe I make it a little bit smaller, but maybe I increase the density a little bit. And if I want a preview of what those changes look like, I can hit that right there, the little glasses or the checkbox next to the glasses. So then I can, kind of play around with that and get the display to look like I want. And you can also change the color of the loads, and you can change color of the constraints, etc. All right, there we go. So at that point, I think we are ready to run this model. So let's go ahead and hit run. And I realized I forgot to do one thing that I wanted to do with this model. Kind of worked out in the last example that I did, but this one, let's be a little bit more precise with the model. So let's go ahead and return here. And so when we are looking at shells, we're going to have a number of different stress outputs. We're going to have a von Mises. We're going to have an X tensor. We're going to have a Y tensor, similar to like we do with solids. The thing with that tensor is it's not necessarily aligned to the global X and Y of the model. Granted, I drew this model in the XY plane, but I just as well could have drawn it in, say, the YZ plane. But when I go to look at my results, my stress tensors, I would still have a stress tensor in the X and I would have a stress tensor in the Y. That is local stress tensors to the shell element. So each one of these elements has a local X direction and a local Y direction. And you can and you probably should define what that orientation is when you are working with shells, if you're going to look at local stress tensors. Again, if you're going to go with a von Mises result or maybe a max or min principal result, it's not as critical. In 3D models, we're generally looking at like a von Mises result or a principal result. But with these shells specifically, what we want to look at as a tensor. So I'm going to right click here where it says analysis 1, and I'm going to go new, and this is where we define that orientation, and we're going to say material orientation, right? And then there are multiple ways for you to do this, and basically what I'm going to do is orient the U direction. In this input dialog, yeah, it's a little bit confusing. I'll give you that. Here in this dialog, they call it the U and V direction. That corresponds to your local X and Y sequentially directions of these shell elements. So let's define the surface U direction, and we'll go ahead and select the geometry. So now it should be displaying for me the local U, which would be the local X direction on those shell elements. And you can see all the arrows pointing in each one of those elements, and it is now aligned with the X. So when I take a look at the stress tensor for the X, that's telling me that is the X of each one of these elements. That is the direction of each one of these little arrows. And it does now, or is now, aligned with the global X direction as well. So that just makes it a little bit easier to, I guess, keep straight when I'm looking at the results, that when I look at the X tensor direction, it is in fact aligned with the global X, and then that would mean the V direction, or the Y tensor would be aligned with the global Y direction, right? All right, let's go ahead and run that again, just in case that wasn't what the program had chosen. Could be a mismatch. We don't know what the program would have utilized before because we hadn't defined it. All right, so here we are in our results, and it is, again, displaying for me a von Mises stress by default. And what we want to do is take a look at the X normal direction, right? So there is my X normal, and we have an output value of 70,087. So let's bring our spreadsheet over. And theoretical value, or theoretical result, was 71,460, so we look pretty close to that. 70,087, plug that in, hit enter. So we're just under 2% different. Still pretty darn good. And let's take a look at the displacement. Our displacement value, we're going to take a look at total displacement, and that's 0.3081. We do want to take a look at the, what am I trying to say? The total displacement. Sometimes when we look at these validation models, it's asking for just an X or Y or Z. So minus 0.3081. I typed that in very wrongly. 0.3081. There we go. And we're 0.2% different on the displacement output. So I would say that's quite good agreement in that model. If you're kind of tired of seeing flat plates, you're like, Mike, let's take a look at some different stuff. I'm happy to let you know that when we do our next validation, my intention is to do a modal analysis, or natural frequency, normal modes, whatever you want to refer to it, all common names that FEA programs use. So make sure to tune into the next video if that is something that would interest you. I hope you enjoyed this one and got something out of it. Thanks for watching. Have a great day.